Welcome students to the fifth lecture on the chapter Atoms. In lecture 4, we had discussed the expression for energy of an electron in nth orbit of hydrogen atom based on Bohr's theory. We calculated the values of the energy of an electron in different orbits. We also try to understand what means by the ground state, what is first excited, second, third and furthermore excited states. Based on the values of energy of an electron in different orbits, we constructed a diagram called energy level diagram. We also try to understand the difference between the energy level diagram and the physical existence of orbits. And finally, we derived an expression for wave number. Wave number of a photon which is emitted due to the transition of an electron from higher energy level to lower energy level in the hydrogen atom. In this lecture, we move further to discuss something called atomic spectra, which is obtained due to the emission of various number of photons when an electron makes a transition from a particular energy level to the lower energy level. It leads to the series of spectral lines. So hence we will discuss the spectral series of hydrogen atom. We will also be discussing the excitation and ionization phenomenon that occurs in an atom. And finally, we'll try to explain the Bohr's second postulate with the help of de Broglie's hypothesis. That is de Broglie's explanation for Bohr's second postulate or quantum condition. So let's begin with atomic spectra. Now here we have the discharge lamps of various gases. So we have a helium discharge lamp, neon, argon, krypton, xenon, hydrogen, deuterium, nitrogen, oxygen and mercury. So when the light from discharge lamp is made to pass through a prism, the light gets dispersed and we get the colored lines on the dark background screen. So this pattern of colors that we get on the screen is called spectrum. When an atomic gas or vapor, if it is excited at low pressure by passing the electric current through it, the emitted radiations has a spectrum which contain a specific wavelength only. Thus, a spectrum of this kind is called atomic emission line spectrum. Try to understand, it is atomic emission line spectrum. Now, it consists of the bright lines on a dark background. So, here we have the atomic emission line spectrum of various elements. We have that of a hydrogen, we have that of a helium, we have for argon, nitrogen, neon, mercury and carbon monoxide. So what we have is we have a dark background and then we have characteristic lines. Whenever it is an elemental spectrum, whenever it is an atomic spectrum, what we have is we have sharp lines as we find in hydrogen, helium, argon, neon and mercury. Whereas in nitrogen and carbon monoxide, what we find is we find bands. So basically it is not atomic spectrum, it is molecular spectrum. That's what the difference is. Now all these are below something called continuum. So the first line we have continuum and below the continuum we have different characteristic lines called atomic emission line spectrum. The hydrogen is the most simplest atom and hence its spectrum is also very, very simple. So we try to understand the phenomenon of spectra, atomic spectra, by taking hydrogen as an example. Now let us discuss the spectral series of hydrogen atom. How do they occur? So we have different energy levels of hydrogen atom with principal quantum number n is equal to 1, 2, 3, 4, 5, 6, 7, and let the last be the one which is very, very far with quantum number infinity. Now we have studied the values of energy of these different energy levels. The first energy level is of minus 13.6, then minus 3.4, minus 1.51, 0.85, 0.54, 0.38, 0.27, up to 7th energy level, and E infinity, infinite energy level, will have the energy 0 electron volts. So all these are in electron volts. Now, we know that the expression for wavelength using the Rydberg constant, we have 1 upon lambda is equal to R into 1 upon N2 square minus 1 upon N1 square, where nu bar is the wave number, lambda is the wavelength, R is called Rydberg constant, N2 is the principal quantum number of lower energy level, N1 is the principal quantum number of higher energy level. Now taking this expression into account, we will try to discuss the spectral series of hydrogen atom. The first series, spectral series of hydrogen atom is called Lyman series. So the Lyman series is the one which is obtained when an electron of hydrogen atom makes a transition from any of the higher energy levels, say N1 is equal to 2, 3, 4, up to anything N, to the first energy level, that is N2 is equal to 1. So this gives us the Lyman series. Now what we mean to say is any transition from any of the higher energy levels to first energy level. So N1 is always more than 1, whereas N2 is always equal to 1. If I put the respective values of N1 and N2 in the above equation, I get the expression as, so it is represented by the formula as 1 upon lambda is equal to R into 1 upon 1 square minus 1 upon N square, where N is anything more than 1. So the Lyman series lies, the wavelength that we get for Lyman series makes it to lie in ultraviolet region of electromagnetic spectrum. Now, the frequency of the Lyman series would be highest when the transition is from infinity to first level, whereas the frequency is least when the transition of an electron is from second to second energy level to first energy level. Whereas when it comes to wavelength, the wavelength is minimum when the transition is from infinity to 1, and the wavelength is maximum when the transition is from second energy level to first energy level. So therefore, the maximum wavelength for Lyman series is 1216 angstrom knot, which is due to the transition of an electron from second energy level to first energy level, whereas minimum wavelength is 912 angstrom knot, which is due to the transition of an electron from infinity to first energy level. The minimum value of wavelength is also called series limit. The transition from infinity to 1 gives out a wavelength, and that wavelength is also called series limit. Series limit of Lyman series is 912 angstrom knot. Let's move on to the next series. The second series, spectral series of hydrogen atom, is Balmer series. The Balmer series is the thing which is obtained when an electron of hydrogen atom makes a transition from any of the higher energy levels, that is N1 is equal to 3, 4, 5, 6 and so on, to second energy level, that is N2 is equal to 2. It is represented, so any of the higher, so transition from any of the higher energy level to second energy level. It is represented by the formula 1 upon lambda is equal to R into 1 upon 2 square minus 1 upon N square. We get it on substitution of N1 and N2. Now, Balmer series lies in visible region of electromagnetic spectrum. Okay, so the series of hydrogen atom that we can see is associated with the Balmer series. The maximum wavelength that is emitted is 6563 angstrom knot, which is due to the transition of an electron from third energy level to second energy level. Whereas the minimum wavelength that is emitted is 3646 angstrom knot, which is due to the transition of an electron from infinite energy level to second energy level. So hence, the series limit of Balmer is 3646 angstrom knot. After Balmer, we have the third series, which is called Paschen series. When an electron of hydrogen atom makes a transition from any of the higher energy levels, that is N1 is equal to 4, 5, 6, 7 and more, to third energy level, it gives Paschen series. So that is from infinity to third, 7 to third, 6 to third, 5 to third, 4 to third. Right? So it is represented by the formula 1 upon lambda is equal to R into 1 upon 3 square minus 1 upon n square. The Paschen series lies in near infrared region of electromagnetic spectrum. The maximum wavelength emitted is 18,451 angstrom knot due to the transition of an electron from fourth energy level to third energy level. And the minimum wavelength emitted is of wavelength 8107 angstrom knot due to the transition of an electron from infinity to 3. So the series limit is 8107 angstrom knot. After Paschen series, the next series of hydrogen atom is bracket. When an electron of hydrogen atom makes a transition from any of the higher energy levels, N1 is equal to 5, 6, 7 and so on to fourth energy level, that is N2 is equal to 4, gives bracket series. So electron transition from higher states to fourth state. It is represented by the formula 1 upon lambda is equal to R into 1 upon 4 square minus 1 upon n square. The bracket series lies in mid-infrared region of electromagnetic spectrum. The maximum wavelength emitted is 40,477 angstrom knot due to the transition of an electron from fifth orbit to fourth orbit, fifth energy level to fourth energy level. And the minimum wavelength emitted is of wavelength 14,572 angstrom knot due to the transition of an electron from infinite energy level to fourth energy level. So the series limit is 14,572 angstrom knot. So after bracket, the fifth series of hydrogen atom is Pfund series. This electron of an hydrogen atom, when it makes a transition from any of the higher energy state, say 6, 7, 8 and so on, to the fifth energy level, that is N2 is equal to 5, gives us Pfund series. So it is represented by the formula 1 upon lambda is equal to R into 1 upon 5 square minus 1 upon n square. Pfund series lies in far infrared region of electromagnetic spectrum. So the maximum wavelength emitted is 74,515 angstrom knot due to the transition of an electron from fifth energy level to fourth energy level, sixth energy level to fifth energy level. So there is a mistake here, it is sixth to fifth and lambda minimum to infinity to fifth. It is the series limit for the Pfund series. So these 5 are the spectral series of hydrogen atom: Lyman, Balmer, Paschen, bracket and Pfund. Lyman series is due to the transition of an electron from any of the higher energy states to 1. Balmer is due to the transition of an electron from any of the higher energy state to 2. Paschen is due to the transition of an electron from any of the higher energy state to 3. Bracket is due to the transition of an electron from any of the higher energy state to 4. and fund series is obtained due to the transition of an electron from any of the higher energy state to fifth energy level. So these were the spectral series of hydrogen atom. Now let's discuss the phenomenon of excitation and ionization. Now we know that whenever an electron jumps from higher energy state to lower energy state, so when an atom absorbs the energy, electron jumps to higher energy state, and when it comes back, it gives out the same amount of energy outwards. So thus, excitation is the process of transferring an electron from its orbit to higher orbit. In any of the atom, the transferring of an electron from its orbit, stationary orbit, to higher orbit is called excitation. The energy required to transfer an electron from its orbit to higher orbit is called excitation energy, whereas the accelerating potential which provides an electron sufficient energy to jump from inner orbit to one of the outer orbits is known as excitation potential, which is denoted with the letter V. So excitation is the phenomenon in which an electron makes a transition from ground state to any of the excited states. That is, electron jumps from first orbit to, in hydrogen atom, from first orbit to any of the higher orbits, say 2, 3, 4 and so on. And the energy required to make an electron to jump to higher orbits is called excitation energy, and the accelerating potential which provides sufficient energy to make this happen is called excitation potential. Now for hydrogen atom, energy of first orbit is 13.6 electron volt, whereas energy of an electron in second orbit is 3.4 electron volt. So therefore, the energy required to excite an electron from n is equal to 1 state to n is equal to 2 state is E is equal to E2 minus E1, which is equal to 10.2 electron volts. Whenever an atom absorbs 10.2 electron volts of energy, an electron in its first orbit jumps to second orbit. So this illustration will help us in understanding what do we mean by excitation. So not only this, the electron can jump from first to third, first to fourth, first to fifth, anywhere in hydrogen atom. And its corresponding energy required to make that respective transition will also goes on increasing as the energy difference between the two orbits goes on increasing. This was excitation. The next phenomenon is ionization. If the atom obtains sufficient energy, then there is a possibility that the electron can move out of the atom and can become free. So the ionization of an atom is the process of removing an electron from the atom. The minimum energy required to remove an electron from its ground state of the atom is called ionization energy. And the minimum accelerating potential which provides an electron sufficient energy, sufficient just to remove it from the ground state is called ionization potential. So when an electron is removed from an atom, the atom gets converted into an ion. So hence the word ionization. For hydrogen atom, ionization energy is equal to the energy required for an electron to rise from ground state, that is n is equal to 1 to continuum state, that is n is equal to infinity, from first level to infinite level. So therefore, the energy required is E is equal to E infinity minus E1, that is 0 minus of minus 13.6, hence plus 13.6 electron volts. The ionization energy of an hydrogen atom is 13.6 electron volts. So this was the concept of excitation and ionization. If the electron goes to higher orbits from the ground state, then it is called excitation. If the electron becomes free from the ground state, then it becomes ionization. Let's move to the last topic of discussion, That is de Broglie's explanation for Bose's second postulate. Now, whenever a fixed string is plucked, only those wavelengths survive which have the nodes at the end and form the standing wave in the string. It means that in a string, standing waves are formed when the total distance traveled by the wave down the string and back is integral multiple of wavelengths. So this is something that we have learned in the chapter Waves of class 11th. So here we have a circular string and the wavelength can survive only if it gets oscillating in this form. Now let us consider a circular loop of radius r consisting standing waves. So now if it will have standing waves if and only if its circumference, that is 2 pi r, is equal to n into lambda. So for a circular loop of radius r, it consists of standing waves only if its circumference 2 pi r is equal to n times of lambda, because we have to get the node to node. The value of n goes as 1, 2, 3, 4 and so on. Now, here we have a diagram in which we have n is equal to 1, n is equal to 2, n is equal to 3 and so on. So when n is equal to 1, if it is the circular loop, okay, resembling our first circular orbit of an electron, then if it is plucked and if the disturbance can be created, then it can have one wave, one crest and one trough. When it comes to the second orbit of an electron, then when n is equal to 2, the possible value of n, since it is 2, it can have two waves, two troughs and two consecutive crests. So it can have two nodes. So similarly, as n increases, we get this kind of pattern. So for an electron moving in first orbit with radius r1, which is here, 2 pi r1 is equal to lambda. 2 pi r1 is equal to lambda. Similarly, for an electron in second orbit with radius r2, we can write 2 pi r2 is equal to 2 lambda. For an electron moving in third orbit with radius r3, we have 2 pi r3 is equal to 3 lambda. We can generalize this to nth orbit as 2 pi rn is equal to n lambda. So therefore, for an electron in nth circular orbit of radius rn, the total distance of the circumference of the orbit is 2 pi rn. Thus, 2 pi rn is equal to n times of lambda, where lambda is the de Broglie wavelength of an electron moving in nth orbit. De Broglie wavelength is given as per the hypothesis as lambda is equal to h upon p, which is equal to h divided by m into Vn, where m is the mass of an electron and Vn is the velocity of the electron in nth orbit. So on equating the equations, we get 2 pi rn is equal to n into h divided by m into Vn. Or on simplification, we can write m into Vn into Rn is equal to nh upon 2 pi. Now, m into Vn into Rn is the angular momentum of an electron revolving in nth orbit of hydrogen atom, which is equivalent to n into h divided by 2 pi. Thus, the de Broglie's hypothesis is used to obtain the Bohr's second postulate of quantization. Thus, the de Broglie hypothesis provided an explanation for Bohr's second postulate for the quantization of angular momentum of orbiting electron. The Bohr's quantum condition says that all orbits are not possible, only those orbits are possible in which an electron have an angular momentum of nh upon 2 pi, which is obtained using de Broglie's hypothesis. So try to work out on all these things that we have discussed in this session, starting from atomic spectra, what it is, how it is obtained, what kind of atomic series, atomic spectrum we get for different elements, Then we chose the simple atomic spectrum, that is of hydrogen. Then we tried to understand the different spectral series that we get from hydrogen atom due to the transition of electrons from the respective energy levels to the respective energy levels. We tried to understand the ionization and excitation phenomenon of an atom. And finally, we provided the de Broglie's explanation for Bohr's second postulate. With this, we finish the discussion of the chapter atoms. In the next lecture, we will be dealing with the numericals associated with these. So this was the chapter atoms. Thank you.